Today, we're going to pull back the curtain on the hidden dance of alkanes. These are the
Subscribe, please.
secrets. And today, we're going to pull back the curtain on the hidden dance of alkanes. These are the fundamental skeletons that literally build our world. Okay, let's get into it. All right, so our story starts at the very beginning, with the molecules that form the framework for pretty much everything organic. These are chemistry's simple skeletons. Take a look at this. This is methane. Looks simple, right? 1 carbon, 4 hydrogens. But don't let that fool you. This little guy is the blueprint for a massive family of compounds we call alkanes. From the natural gas that might be heating your home to the plastics in your phone, it really does all start right here. So, what is an alkane really? Well, think of them as the ultimate minimalists of the molecular world. It's just hydrogen and carbon, connected by these super strong, super stable single bonds. This simple setup gives them this perfect tetrahedral shape with a bond angle of 109.5 degrees. And trust me, you're going to want to remember that number. It's going to be a huge deal later on. So we have our basic blueprint. But how do we get from one tiny methane molecule to the massive, complex structures that make up our world? How do chemists actually play the role of molecular architects, building bigger and better skeletons? It's really like having a box of molecular Legos, isn't it? So how do you snap them together to build something totally new? Turns out, chemists have some seriously cool tricks up their sleeves for exactly this. One of the absolute coolest tools in the toolbox is the Corey-House reaction. It's kind of like a high-tech molecular construction kit. First, you build this special connector piece. It's called a Gilman reagent. Then you just grab the 2 different carbon chains you want to join, and bam! The Gilman reagent snaps them together. It's an incredibly versatile way to build all sorts of custom-made alkanes. Now, because alkanes are built with those super strong single bonds we just talked about, they're incredibly stable. They're generally, well, kind of unreactive. But that doesn't mean they're invincible. If you push them just right, you can force them into a pretty dramatic reaction, totally against their will. Alkanes actually have a nickname, paraffins. It's Latin for little affinity, which is really just a fancy way of saying they don't like to react with much of anything. Their electrons are all locked down tight in those strong bonds, making them super tough to crack. But, don't let their chill vibe fool you. Because with just a little nudge, a bit of light or heat, you can kick off this wild chain reaction called halogenation. This is where you violently swap out a hydrogen atom for a halogen, like chlorine. It's this high-energy molecular switcheroo, and it's super important for making things we use every day, like PVC plastics and even some anesthetics.
So, it all starts with a spark. And I mean that kind of literally. A blast of UV light comes in and just rips a chlorine molecule in 2. What you're left with are these 2 superreactive chlorine atoms called free radicals. These things are unstable. They've got an unpaired electron, and they will do anything to find a partner for.
And this is where things really take off. This is the chain part of the chain reaction. A chlorine radical slams into a methane molecule and just rips off a hydrogen. That creates a new radical, a methyl radical. This new guy then goes and attacks another chlorine molecule, and the cycle just keeps going and going and going. It's a cascade of chaos. So how does all this chaos finally stop? Well, it's called termination. Sooner or later, 2 of these lonely, super-reactive radicals are going to bump into each other instead of a stable molecule. When they do, they combine, form a nice, stable bond, and effectively cancel each other out. And just like that, the chain reaction just fizzles out. Okay, so we've been talking about how these molecules react, which kind of implies they're just sitting there waiting. But that's not the whole story. The diagrams we draw, these static stick figures, they're a bit of a lie. In reality, these molecules are always moving. It's time to pull back the curtain on the hidden molecular dance. See, that single bond connecting the carbons? It's not rigid at all. It acts like an axle, letting the ends of the molecules spin around freely, constantly. This constant spinning creates different shapes, or what we call conformations. The 2 big ones to know are the staggered form, that's where all the atoms are spread out nice and comfy, and the eclipsed form, where they're all lined up and getting right in each other's personal space. So why does any of this spinning matter? Well, meet the villain of our story, torsional strain. When the molecule is in that ellipsed shape, the electron clouds around the hydrogen atoms are shoved right up against each other. And just like when you try to push the same poles of 2 magnets together, they repel. They push each other away. This creates a ton of instability and jacks up the molecule's energy. It's just really uncomfortable for the molecule. This graph shows you exactly what's happening. Think of it like a roller coaster. The low points, the valleys, that's the stable, staggered shape. The molecule loves to just hang out there. The peaks are those unstable, high-energy eclipsed shapes. So to get from one comfy valley to the next, the molecule has to climb this energy hill and briefly pass through that uncomfortable peak. It's constantly moving, but it definitely prefers to spend most of its time in those low-energy valleys.
Okay, let's take everything we've just learned and add one last fascinating twist. We've looked at straight chains, we've seen them dance and spin. But what happens if one of those chains bites its own tail and forms a ring? This creates a completely new kind of problem.
Hey, remember that magic number I told you to remember? 109.5 degrees? Well, that's carbon's happy place. That's the angle it wants to be at. But when you force these atoms into a small ring, you can't have that. Look at cyclopropane. The angles are crushed down to 60 degrees. Can you imagine the tension? Cyclopentane, on the other hand, look at that. It's almost perfect. It's a happy, relaxed ring.
And this chart just makes it crystal clear. Just look at the insane amount of strain packed into cyclopropane. It's like a tightly coiled spring just begging to pop open. Cyclobutane is pretty strained too, for sure, but then you get to cyclopentane, and the strain practically disappears. It's found its happy place, almost perfectly stress-free.
And this angle strain, as it's called, has real-world consequences. It's not just some number on a chart. It makes these small rings, like cyclopropane and cyclobutane, way less stable and way more reactive than their straight-chain cousins. They are literally wound up with energy, ready to snap at the very first chance they get.
So from simple, straight skeletons to constantly spinning tops and super strained rings, it's pretty clear that a molecule's shape is its destiny. It controls how it moves, how it reacts, and ultimately how it builds the entire world around us. It really makes you wonder, doesn't it? What other huge secrets are hiding right there, in plain sight?
Thank you for watching my video. Please like, subscribe, and hit the bell icon.